Imagine a simple, almost unremarkable photograph. Rows of gray drone fuselages standing quietly in a dimly lit workshop. Faint overhead lights, a couple of workers in plain overalls moving methodically. No roaring conveyor belts, no army of industrial robots like you'd see at Boeing or Airbus. Just quiet, focused work. And right here, if you pay attention, is where the real story begins. For a long time now, the common narrative has been very simple. Shahed drones are nothing more than cheap Iranian copies of Chinese designs. Low cost, low tech, built in garages or primitive workshops, and therefore easy to produce in huge numbers and equally easy to shoot down. It sounds logical. It fits the picture most people already carry in their heads. But the moment you look at how these drones are actually made on the ground, that comfortable explanation starts to fall apart. This is not classic mass production. It's also not some amateur backyard operation. What's really happening is small series assembly. Careful, almost handcrafted in places, but guided by a very precise understanding of which corners can be cut and which ones absolutely cannot. Every step has a reason. And hidden inside that process is one small engineering decision that quietly gives these drones noticeably more range than their simple appearance would suggest. Let's start with what we actually see when photos or videos from the factories occasionally surface. Composite materials for the body. A relatively basic piston engine. Wings that fold for easier transportation. On the surface, it looks exactly like the cheapest possible way to build a one-way attack drone. Most analysts look at it and immediately conclude, no wonder they lose so many. They're disposable by design. But here's where the numbers stop matching the story. The real-world range these drones regularly demonstrate, often well over 2,000 kilometers on a single low-altitude flight, is significantly higher than standard aerodynamic calculations would predict for this kind of lightweight and simplified layout. Something doesn't add up if you only look at the obvious parts. The answer isn't hidden in some revolutionary new engine or secret guidance package. It's much more subtle. It sits in the wing structure, specifically in how the folding mechanism is engineered. When you design a folding wing for transport, you almost always create a potential weak point at the hinge. Constant vibration, flexing, material fatigue over long flights at low altitude, where turbulence is almost permanent. These things add up fast. In traditional aviation, engineers solve this problem with heavy metal reinforcements, complex locking systems, or by simply making the wing stronger and heavier. All of that adds cost, weight, and complexity. The people building the Shahed took a quieter and smarter route. They developed a specialized composite joint at the folding point. At first glance, it looks deceptively simple. Thin, lightweight, nothing flashy. But the real magic lies in the precise orientation and layering of the carbon fibers inside that joint. When the wing is unfolded and locked for flight, those fibers create a connection that behaves almost like a single solid piece rather than a hinged assembly. The stiffness is remarkably high for the weight involved. At the same time, when folded, the joint adds almost zero extra mass or bulk. It's one small detail. But that single detail allows the entire wing to maintain structural integrity during many hours of flight through turbulent air close to the ground. Exactly the conditions where most cheap drones would start to shake themselves apart or lose aerodynamic efficiency. And here's where it gets really interesting. This solution doesn't require cutting-edge Western machinery or billion-dollar clean rooms. It can be manufactured in a relatively modest facility equipped with good molds, proper temperature control, and technicians who truly understand composites. They don't need to churn out thousands of drones every month. A few hundred, built carefully and consistently, turns out to be enough. Each machine comes out with predictable performance because the most critical weak point has been quietly engineered away. That's why, even though many Shahed drones are indeed intercepted and destroyed, the ones that get through continue to show ranges that surprise military observers. It's not magic. It's not some mythical genius Iranian engineering. It's a very focused, practical solution to one specific engineering problem, and they deliberately refuse to over-engineer everything else around it. Of course, none of this makes the drones invulnerable. Modern air defense systems are getting better at detecting and neutralizing them. Losses are real and often heavy, but this hidden margin in the wing design helps explain why the threat refuses to disappear as quickly as many predicted. It's a classic case of clever trade-offs. They sacrificed certain performance characteristics to protect the ones that matter most for their particular mission. So the next time you hear someone casually dismiss Shahed drones as crude, low-tech junk, keep this in mind. Sometimes the most effective tricks aren't the loudest or the most expensive. Sometimes they're quiet, almost invisible improvements in a place most people never think to look. In tomorrow's video, we'll take the next logical step and examine how all of this is directly connected to oil prices, why they are rising right now, what's really happening in the Strait of Hormuz, and how one small detail in tanker design can suddenly become the most important factor in the entire energy equation. Because the drones are only the visible tip of a much larger chain reaction that's playing out right now. What do you think about this kind of practical, no-nonsense engineering approach? Is it smarter to build something simple but reliable, or to chase perfection and risk unnecessary complexity? Let me know your thoughts in the comments. I read every single one.